Okay, good morning. So I want to do a simple expansion of kernel function. First, let me explain about the classical things, the heat kernel. So first, Fetterman looked at the heat kernel and tried to do the analogy for the Bergman kernel. So it's better to start with the classical case and what should be changed. So M and G, so this is an n-dimensional compact Riemann manifold. Then heat kernel is given by, say, Laplacian. So this is a positive Laplacian today. They take eigenfunctions. So these are Pj to 1 to infinity also normal eigenfunctions. So it's a complete also normal system for the L2 space of function on this compact manifold. So I assume that this is positive. Okay. Zero means harmonic, and so it goes up. Then the heat kernel on the diagonal. So I only consider the Bergman kernel on the diagonal. So let me just explain this case. Is defined by sum of these eigenfunctions squared. Okay. So it looks like Bergman kernel, but here's a slight difference. So I need to put this spectral term to make it convergent. So there's no inside. So this is just one manifold, and we have time variables. If time variable is positive, we have convergence. When t goes to 0, it diverges, because it's a heat kernel should diverge. It concentrates to a point, so you have to have a delta function. It diverges. Okay, so when compute the asymptotic behavior as p tends to 0. So it starts with, there's some constant depending only on dimension, and then normal to be 1, same j, it's okay, to infinity pj x tj, and these functions, these are smooth m, and these are local invariants of metric G. So local invariance means, this means in normal coordinate, at a point P, this value is a polynomial in Taylor coefficient of this G at P. So G has component Gij, and in normal coordinate, you can expand each component as a power series and look at all these coefficients. So at normal form, at geodesic normal form, this function should be represented by a universal polynomial. Universal means independent choice of manifold. There's some universal polynomial that express this. But so these Taylor coefficients, G at P, can be written as a in curvature. of G. So here curvature, coefficient in curvature here. I mean, so R is a curvature. It has 4 indices, I, J, K, L. And then if you apply covariant derivative P times, then you have P indices 1, I, P, and J, K, L, M. So you have more indices. So consider all such components and write in some bases coming from the normal coordinate. Then these coefficients, this polynomial can be written in terms of the components of these. So this can be seen as an invariant polynomial. So phi j p is a ON invariant polynomial in curvature. So maybe jet of, so as I differentiate curvature, it's better to say jet of curvature. Okay, so this ON coming from the choice of normal coordinate. So normal coordinate is not unique. This is determined up to orthogonal group functions. For each choice of orthonormal basis, you have a normal coordinate. You can rotate the orthonormal basis by orthogonal group. It's almost a definition. So everything should be invariant under orthogonal group action. So this is an invariant polynomial in these components, which is invariant of this group. Then one can use Weyl's classical invariance, right? So this ON is a classical group, and it is well known that such invariant can be written in terms of complete contraction. Contraction of R, P1 applied to curvature, P2 applied to curvature, and so on, to PS applied to curvature. So it has many indices. So you have to contract this tensor into a scalar function because phi j is a scalar function. So there should be even number of indices, and you take a pairing and contract into scalar by using the metric. So theory shows that phi j is a linear combination of such terms. Okay. So moreover, if you consider scaling of constant scaling, so if you change G by, I use lambda for spectrum, so okay, C, G, C positive, constant. If you scale by constant, everything is scaled, and each coefficient also scales nicely. So just observing the scaling factor, you can say that this phi j for phi j, we have, so these j should be s plus half of p1 plus p2 plus ps. So the number of derivative is controlled by this j. So if j is small, you cannot differentiate much, or the terms, number of terms should be small. And since the number of indices should be even, so this is an even number, so you divide it by 2. Okay. Just by this observation, you can write down the coefficients. So gamma, so example, maybe go here. So gamma 1 is the first one. For gamma 1, you have to take j equals 1. So S should be at least 1. Then P should be 0. So then S equals 1, or P equals 0, P1 equals 0. That's mean no derivative, just contraction. Some constant times contraction of curvature. This is a scalar curvature. This is scalar curvature. So scalar curvature is by definition R, I, J. No, this is a scalar. I, J. This is Q, I, J. Okay, it should be the same. So repeated indices is summed. So maybe Ij, it's better to write I, K, I, J, K, L, and G, I, K, G, J, L, and sum over I, J, K, L. So this sum lift up indices. So this K is lifted up to I, and this L is lifted up to J. So this is an Einstein summation convention with raising or lowering indices. So this is scalar curvature. Now gamma 2, then you have case S equals 2, and then P1 equal P2 equals 0. So the choice is C1, scalar curvature squared plus just a norm square of the curvature itself plus norm square of the rich tensor. So this means when you oh, sorry. I changed. This should be fine. Yeah. Fi. Change notation. Okay. So the second one is, so S equal 2 means you have two terms with no derivative. There are two ways to make complete contraction. The first one is contracting, three ways. So this is contracting within each tensor. This is contracting four indices to the other four indices here. So this one is contract once here, and then contract each other. So we have three choice, and also S equals 1, P1 equals 2 should be plus C4 Russian S. Yeah. So this is the only possibility. So you have four terms with four universal constant. Universal means it, in this case, it's just number, also independent of the dimension. It is not shown in this argument, but these are constant, at least independent choice of manifold or metric. So we can continue. And to determine these coefficients, you have to do some calculation of the heat kernel. But we know that this is a universal constant. You can do this for very special choice of metric. So for a very special choice of metric, it is sometimes easier to compute heat kernel, and then it is possible to identify these. And Peter Gilkey did much of these computation using computer in 60s, 70s. Yeah. Still, these are done by computers, I think. So if your computer have enough memory, you can continue. So there's the algorithm, algebraic. Okay. So after seeing this, Fetterman thought that maybe we can do the same thing for the Bergman kernel. Okay. But there are several things which goes differently. Okay, there's no time variable t in the Bergman Kernel case. So defining function is a choice, but then it's not the product of the boundary times distance from the boundary. It's not so simple. So now return to the Bergman Kernel. So the important thing is the biholomorphic transformation rule. So today I don't use 1 and 2 because I have too many indices. So I prefer this omega and omega tilde biholomorphic. So always biholomorphic. So anything on omega is omega tilde has tilde. This is a Bergman kernel for this domain. So if you prove back by this biholomorphic map, you get this factor. Okay, this is a Bergman kernel for this. So I sometimes write this in other side, so you always make mistake of positive or negative. So today I always keep prove back on left-hand side and the Jacobian term in right-hand side. Okay, so now look at recall the transformation rule of the Monge Ampère solution. This is n plus 1 times 2. Okay, so negative power agree with this. So these are Monge Ampère solution. So it maybe have singularity, but just forget about this for now. Then look at the Bergman kernel for each domain. So there's such a form by Fetterman theorem, and we only look at the term which is determined locally. So this phi contains globally determined terms. So I only consider phi mod O to rho to n plus 1. So this term doesn't give singularity of the Bergman kernel. So this term is not locally determined. So it's impossible to write in terms of curvature. So ignore this. Also, psi mod or rho infinity. This means almost nothing, but I don't consider about the convergence, just formal expansion. So we want to compute these. Then suppose, it's better to write the transformation rule, psi tilde. So this phi tilde has powers of rho here. And comparing these transformation rule, we see that this term is preserved. But we have to ignore this term, so I put this to emphasize this fact. So the way you write in this form is not unique. Yeah. Also, this here is some factor, determinant. Fine. Should be equivalent to the Bergman kernel. Psi. Maybe this term. Okay, these are because these are well defined only up to this order. Okay, so these are the functions in the coefficients. Say we try to expand phi equals phi 0 plus phi 1 rho plus phi 2 rho plus phi n, rho to n, plus globally determined term, and psi equals, so I use rather strange notation, but it will make sense later. So the phi coefficient, the pole type singularity has these n plus 1 coefficients. Then the next one is the log term, so I put the n plus 1 here. Then it starts with 0th order, 1st order, and continue. Okay, so we have a series of functions. It looks like an expansion of the heat kernel, but these phi j are not function on the boundary. These should be function inside and extends smoothly the boundary. So you have to consider the extension together with the boundary value. So you may think that you can write down this as a boundary times some interval. So 0, 1, at least near the boundary. So you want to transform into boundary times interval. But then holomorphic structure will break down. It's impossible. So there's no biholomorphic transformation rule when you write down in this form. So if you just use some decomposition and do Taylor expansion, the coefficients never have such a nice transformation rule. So, but we want to have Pj infinity, writing the same thing here, locally determined by boundary, and Pj tilde pullback should satisfy good transformation rule. Minus 2j Pj. Maybe some error, but just ignore for now. So just comparing the transfer rule of law, so each power gives this negative this positive number, so you should have more negative number. So it makes sense. If rho has that transformation rule, each coefficient should have this transformation rule. So we try to find some nice functions which are locally constructed from the boundary and satisfy this transformation rule. So let me define a shear invariant and of weight W. So W will be, number is functional I boundary omega for each given boundary. It can be real valued or complex valued. Given for each strict convex omega such that two properties. I don't have enough space, so let me continue here. Just writing down the property of each Pj as a definition. So this boundary function is locally by the boundary. So it means polynomial in the Taylor coefficients of rho at each point. I have to be more precise, but it's precise. Maybe I have to introduce normal coordinate to precisely state this, but you can guess what it means. So there's some normal coordinate in this complex geometry. Also, then using that, you can show that this is a invariant polynomial. It's a polynomial in the Taylor coefficients of G in this case and rho in this case. Okay. So this is locally determined or polynomially determined. It's a very strong condition. And if F is biholomorphic, then I of boundary omega tilde pull back by f. So by Fetterman's extension theorem, it has boundary values, so you can pull back the boundary by f. That should be 1 minus 2w. So for each pair, which is by holomorphic, this transformation rule should hold.
This has to be global. I mean, if I a little bit of the boundary.
That's okay. Yes, if you have a local bihomorphic map from here to here, then you can make a strictly pseudo-convex domain here. So it's the same thing. Yeah, this is strictly pseudo-convex. Everything is easy. Yeah, you can localize. Anyway, it's a, yeah, we can start with local statement, but it is easier. So, problem is construct all CR invariant with extension to inside, to at least near the, so CR invariant is just defined on the boundary. So on the boundary, but to do asymptotic expansion, we want to extend to the inside, at least near the boundary. So we want to construct CR invariant in such a way that it naturally extends to the inside, preserving this transformation rule. So it's a very strong requirement that we can do this, almost. So if you can solve this problem, you can inductively construct such expansion. So first one, phi1, phi0, this is a constant. No transformation rule, so just take a constant. Then subtract constant and divide by rho. Then you have some function phi1, which satisfy these transformation rules for j equals 1. Then take that function we successfully constructed. It should agree up to some constant manifold, which is universal. Then consider the difference, and then divide by rho again. Then you get the phi2. So in this way, you can write down. So this is the fundamental question. So we can try this approach using invariant theory to construct everything. But there's no natural curvature on the domain itself because we have constructed Einstein-Kähler metric and Bergman metric. So using Bergman metric is not so good because we want to write down the Bergman kernel. So using Bergman kernel to write down Bergman kernel doesn't help. Okay, maybe possible. That's a good idea. So use Monge-Ampère solution. We can construct Monge-Ampère solution up to some order by explicit procedure. So we can say that we can compute rho up to some order. So use Einstein-Kähler metric. But this is complete. That means it diverges at the boundary. So there's no curvature at the boundary. So that's another problem. So we have to lift up. That's the idea of the ambient metric we did yesterday. One example. So the trivial example is phi0 is weight 0. That's constant. And so psi is a log term coefficient. When you restrict the boundary, is a CR invariant of weight n plus 1. This is highly non-trivial. Writing down this is very difficult. Okay. Usually when you do analysis, in order to compute the n plus 1 term in the expansion, you have to first determine all the first n term, otherwise you can do the next. But by using this method, you can skip and just start with n plus 1, just using invariant theory. That's a good merit for using this. This is Fetterman's idea. So use ambient metric. So recall rho is a Monge-Ampère solution. The smooth approximation or the chain out solution with singularity, whichever, for now, we can consider the difficulty later. So now, this is just this. Lifting function to bundle by putting this scale factor to the boundary. Then G tilde ambient metric for rho is minus dD bar of rho sharp. This is Lorentz here. And this is flat for the model case of the ball. And this gives SUN1 action on the ball. Okay. So we have a metric, then define curvature and its covariant derivatives. We can use Kähler geometry. Kähler geometry. So we have G tilde. So we have a curvature. And connection. So curvature has I, J, K, L. But now we have two holomorphic, two anti-holomorphic indices. Other combination will vanish or have symmetry, so we only have to consider this type. So let me use a notation type 2 for this, because for two holomorphic, two anti-holomorphic. Then apply covariant derivatives. So this comes from Nabla. Nabla gives curvature. So let me define PQ by applying P minus 2 holomorphic derivative and Q minus 2 anti-holomorphic derivative. So this means here's I1 to IP minus 2 is J1 bar to JQ minus 2 bar and IP minus 1. IP JQ minus 1 conjugate JQ. So you have type PQ tensor by this covariant derivative. Maybe you can mix the order, but it doesn't make much change because it's a non-quadratic term in curvature, but you can always sort in this form. So no generality is lost by this, assuming this ordering. So we have many tensors. Now consider Q1, P2, Q2 tensor product, PS, QS, and contract to a scalar. So here, yeah. So this is not, it doesn't work.
Yes,
right?
Right.
So you want to, so this is locally determined, singularity is locally determined. It should be written in terms of CR geometry. So that's a geometry of the boundary. So in order to describe the CR information of this function, you have to expand to see each term. Otherwise, this is just there's no way to relate this function to the boundary. If you take just the boundary value, it's just, in this case, just constant. So you want to see some information first, subtract the constant and divide by rho. Then look at the term. That should be the phi1.
No, I understand that, but I probably the claim that you make,
That
each Pj is locally determined.
Yeah.
Locally determined by the boundary.
Yeah.
I mean, how do we know that?
So this comes from, it's already contained in the program. So in the program, the CR invariant should be constructed in such a way that the normal direction is also locally determined. Yeah. Yes. So far we are doing good things. So this rho is determined locally even for the normal direction. So everything here is determined in all directions locally by the shear geometry. So don't restrict the boundary. All the analysis should be done in all directions. And in the final step, we restrict. Yeah. So everything is done in a neighborhood. So this is in a neighborhood. Okay. So we have scalar function by taking contraction. So in this case, you have to count the number of indices which should be same. So Pj, j equals 1 to s should be j equals 1 to s for Qj. Holomorphic and anti-holomorphic indices should be the same number, otherwise you cannot take complete contraction because metric is ij bar. So it has one holomorphic, one anti-holomorphic indices. So to contract everything, you should have this constraint. Okay. So let me write this W hash. Everything on, so this is on the bundle, so I put hash, like row hash. Okay, this is a function defined up to the boundary to maybe just C. Okay. Actually, we are only looking at so this is omega just near the boundary. So I have to say this is near the boundary always because if you use approximate solution, the inside doesn't much make sense. So just look at near the boundary. So then this is always non-degenerate and Lorentzian, so we can do this calculation. So we get the function on the boundary which is defined at least near the boundary. Okay. So we construct the function on the boundary, but what we need is the function on the domain. So we have to project down this. But since G tilde is homogeneous, so it's hash. So homogeneous means this row hash is homogeneous, clearly homogeneous. And DD bar, this preserves homogeneity. So the curvature itself is homogeneous. There's some nice transformation rule. And these should have the same transformation rule. So you can easily calculate the degree. So if you z naught square, it's always in this separated form. This is in downstairs. So this is a function, in the fiber variable and number. This W equals sigma Pj j equals 1 to s minus s. So in the Riemannian case, we take the half. But here, we don't take half because we only look at half of this. So we have Pj, Qj. So if you sum up everything, you have to take half. But we should not do that. Also, the numbering is different. So I have to minus s, not plus s. This is just coming from that notation. Okay. So you have now we have function on the domain. Then recall the transformation rule. So if you have f lift up. So this is W0. Oh, I have. So that W is weight. This is a variable. Oh, very bad notation. Z naught, Z. And important thing is, so this is Z, and this should be Z naught times determinant F prime to the n plus 1 minus 1. Okay. This is the definition. So if you prove back, so everything, so the metric is preserved by the lift. Okay? Because low hash is preserved by F hash. So the metric is preserved. So the curvature is preserved. So W hash is also preserved. So we should have this. Then by this formula, we should have proof back of this F tilde should be determinant F times n plus 1 minus 2W W. First, we construct invariant function on the bundle, then factor out the fiber variable. Then you have a function which has nice transformation rule. This is the transformation rule we impose for the definition of the invariant with W. So this gives, I should give a name. So restriction to this boundary is a shear let me first call it such W is called Weyl invariant. So Weyl invariant means anything coming from complete contraction and factoring out the Z naught factor. I don't claim that this is a CR invariant or well defined, but this is the definition because this is coming from the Weyl invariant theory. But actually, the invariant theory behind this is not the Weyl's classical invariant theory. We have smaller group, it's called parabolic subgroup, and this is the invariant theory is called parabolic invariant theory, but maybe I have no time to go into the detail about this, but okay, let me state the theorem. Fetterman and Weyl. So Fetterman create everything, and these three people, the invariant theory needed for this. So Fetterman did partially, and they completed in a sense. So the CR invariant of weight W, which is equals or less than n, are given by linear combination of Weyl invariant of weight n. So this theorem contains two parts. So first, we have to check that this is well defined. So the point is that if you start with chain solution, this solution is not smooth. So if you differentiate too many times, it may hit log term, and then the curvature may diverge or doesn't make sense because it's not differentiable. So you have to check that's not, you should not differentiate too much. So if the weight is small, it is bounded by, the weight bounds number of derivatives. So it also depends on number of factors. So you should do the estimate, and this is a safe number. This n is safe. Also, if you start with Fetterman's approximate solution, that is not unique. That is defined only on O to rho to n plus 3, 2 or 3, I don't remember. Okay, so some error term. So if you differentiate rho too many times, it may hit this ambiguity. So then this is not well defined. So you cannot say that this is a CR invariant. So, but up to this weight, everything goes right, and everything is determined locally, and there's algorithms to compute this. So this solves the problem for this weight. So all the boundary value gives CR invariant, and every Weyl invariant comes with extension to the inside by definition. So up to here, unfortunately, actually Fetterman proved that weight n minus 19 weight. This is a very strange number. This is just a technical difficulty. I haven't read his paper. That's very difficult to read. But later, so Eastwood is not much about the representation theory, and Bailey did some coming from physics, and Brown knows both sides, so that they combine everything and prove this, that you can remove this strange number and do the optimal in the sense that ambiguity in law is considered. Okay, so we have theorem, solve the problem partially, so you can write down the expansion. So to n means you can do this for the phi term. You cannot touch the psi because this comes with n plus 1. That's beyond the abstraction. So first term, this is a constant. Weight 0 means constant, and this should be pi to n and fractional. This is due to Hörmander. Just stating again, P1 should be 0 because, so this means W equals 1. So weight equals 1 equals sigma Pj minus 1. J equals 1 to S. But each term, so Pj should be at least 2 because it's a Kähler curvature. So it is bounded by 1. So this is 1, this is 1. So the only choice is Pj is 2. So S equals 1. This means S equals 1 and P1 equals 2. So Q1 equals 2. So only choice is R22 contraction. So this may happen here, but by Monge-Ampère equation, we know that this curvature is Ricci flat. This is. So if we take trace, this is always 0, so you should get 0. Next, here comes non-trivial term. C prime, so square norm of the curvature. So I use the notation of complete contraction, but you should factor out z naught square. Or maybe you can do this. You can just say z naught to be 1. so that this becomes a function in the domain. So this is the first term, and there's no other, because linear term always vanish because it is rich flat. Then phi3 equals some constant 3, 2 squared plus contraction of curvature plus contraction 1 and 2. Two choice. So here we have 1, 2, 3, 12 indices. You have to make pairing without making rich tensor. So there are only two possibilities. And you have 3 terms. So we can continue. And the other step is how to compute this number. This can be done by considering a domain, some nice domain for which you can rather easily compute Bergman Kernel approximately. So for each term, you can do this. Sometimes you need the help of computer, but this is algebraic, so you can do this. And basically, this is the program Fetterman proposed, and it works. Okay. So the next question is what's happened beyond this number? Okay. Beyond that, you have to be smooth, define function more precisely. So basically what we do is not just solving. So Fetterman's idea is just use this. But this is not good enough. So instead, I have to solve the equation like u equals rho plus rho sigma j equals 1 to infinity eta j rho n plus 1 log rho. I put all the singularity. This is a formal sum. Don't consider convergence. Then formally solve this. This has solution. And you can algebraically determine these coefficients. It's not uniquely, but if you take a normal vector field of the boundary, so this solution, this equation with normal derivative to the boundary f. Boundary, this is given for any, so I have to give one more condition. This is a Neumann condition of very high order. This is a degree we lose the uniqueness. Then I have to fix that term. I have to fix by specifying that term. Then this has unique solution. Exists unique u, and that's law. So this law is specified more precisely. It's not unique, but precisely determined. By using that, I can remove using exactly the same technique, I can remove this. But everything depends on this f. Okay, this f. So each double Weyl invariant may depend on F, so I have to put this F. But in this situation, invariant linear combination of Weyl invariant that independent of F. So each term may depend on F, but the linear sum, it can cancel. So if you consider all such cases, that is exactly the CR invariant. So you need one more step to determine which is CR invariant, but I can, this is my theorem. 2000 already, almost 20 years ago. So do everything with additional parameter as a function, then you can remove, and you get nice Weyl invariant with extension, but it has F. But you can use this to expand the log term. You can do the exactly same thing for the psi, and we can prove, say, Ramadanov conjecture for n equal 2 by using that. So maybe I talk about this tomorrow in the beginning. Okay, let me stop.